The orange cycloid wins this race. But keep the tracks exactly where they are, change the medium around the beads, and the blue straight line wins instead. The shortest route starts as a loser and finishes as the champion. What changed? All 4 tracks connect the same 2 points, a horizontal run of 6.78 model units and a vertical drop of 4.52. The blue path is a straight line. The orange path is a cycloid, the classic solution to the ideal Bräckestakron problem. Green drops sharply near the start, while red saves most of its descent for later. Every bead starts from rest. Our numerical model follows a sliding point bead along each sampled curve. Gravity pulls it down the slope, roughness removes tangential acceleration, and drag grows with the square of speed. This is a controlled mathematical model, not a claim that every real rolling ball will behave identically. Before each round, make a prediction. Which advantage matters most? Round 1 removes both friction and drag. This is the condition in which the acycloid is supposed to shine. The result is acycloid at 1.474 seconds, early drop at 1.49 seconds, straight at 1.73 seconds, and late drop at 3.159 seconds. The acycloid beats early drop by only 0.016 seconds. The straight line is shorter, 152 units compared with 8.726 for the acycloid, but it descends gradually. The acycloid sacrifices distance to become steep immediately, converting height into speed earlier. Watch the replay at half speed. Orange opens its advantage near the start, not near the finish. That early speed is why a longer path can arrive first. For round 2, gravity stays fixed at 9.81, while the friction coefficient becomes 0.066. Nothing else changes. The order is acycloid at 1.505 seconds, early drop at 1.53 seconds, straight at 1.823 seconds, and late drop at 4.344 seconds. Friction slows every contestant, but the acycloid still wins. In this simplified model, roughness alone does not erase the benefit of accelerating early. The late drop curve suffers most because its shallow beginning has little tangential gravity available to overcome resistance. This round is important because it prevents us from blaming every future reversal on a vague idea of resistance. We have changed one term and measured the result. Now reset friction to 0 and introduce quadratic drag with coefficient 0.174 in our model. Drag is different from the previous penalty. It grows rapidly when a bead moves quickly. That attacks the cycloid's main strength. The new order is early drop at 1.99 seconds, acycloid at 2.01 seconds, straight at 2.153 seconds, and late drop at 3.628 seconds. The winner is now early drop. This is the first reversal. The steep early paths build speed quickly, but that speed creates a stronger drag penalty. The straight route accelerates more slowly and travels less distance. It has not won yet, but the gap has changed direction. The experiment is no longer asking which path falls fastest in an ideal vacuum. It is asking which path balances acceleration, distance, and speed-dependent loss. The final combines the roughness from round 2 with a much denser medium. Friction is 0.066, and the drag coefficient is 1.548. The measured order is straight at 4.825 seconds, early drop at 5.467 seconds, acycloid at 6.683 seconds, and late drop at 7.822 seconds. Straight wins in 4.825 seconds, 0.642 seconds ahead of early drop. Compare the two main contestants directly. A cycloid changes from 1.474 seconds in the ideal round to 6.683 seconds here. Straight changes from 1.73 to 4.825. The route that lost because it accelerated too slowly now wins, because it is short and never pays as much for extreme speed. There is no contradiction. The word fastest always depends on the rules. The predetermined cycloid minimizes travel time for an idealized point moving under uniform gravity without these added losses. Our later rounds solve a different problem. Think of the total time as a competition between three effects. First is early acceleration. A steep opening builds velocity while much of the journey remains. Second is path length. Every extra piece of track takes time and creates more opportunity for resistance. Third is speed cost. Quadratic drag punishes high velocity much more strongly than low velocity. Orange dominates the first effect. Blue dominates the second and avoids the worst of the third. Green sits between them, so it becomes the temporary winner before the straight line takes over. The red late drop curve has neither early speed nor minimum distance, which is why it remains behind. The animation is not choosing a winner for drama. It is displaying the finish times produced by the same numerical integration used to generate this script. A 4-round story can hide where the change actually occurs, so now sweep the drag coefficient through 81 equally spaced samples from 0 to 1.8. Keep gravity at 9.81 and friction at 0.066. The measured crossover sequence is: a cycloid changes to early drop between 0.113 and 0.135. Then early drop changes to straight between 0.405 and 0.427. Those are sampled intervals, not invented exact constants. A finer simulation could narrow them. The important feature is the order. Low drag rewards the cycloid's early acceleration. Intermediate drag favors the early drop compromise. High drag eventually makes the shortest path fastest. The continuous graph confirms the explanation we formed from 4 individual races, instead of merely repeating the result. So the answer is conditional. On the smooth ideal track, a cycloid wins. Under the final rough, high drag rules, straight wins. The code generated the geometry, measured every race, located both crossover intervals, and built this episode from those results. The next experiment changes the model again. Replace the sliding points with rolling balls that have rotational inertia. Will the same crossover survive?